Greetings, folks. Welcome. The practice of statistical inference involves using information from a sample to say something about a population. One common application of statistical inference is using information from a sample to estimate a population proportion value. So the idea here is you first calculate a sample proportion. Again, you can go out and collect data on a random sample of people or whatever you're studying and calculate a percentage value. And then you put a margin of error around it. Here you see the formula. You have an uppercase P on the left-hand side. It represents the population proportion. And that population proportion is equal to a lowercase p, which is a sample proportion, plus or minus a margin of error. In a different video, I'll show you the exact formula we use to calculate this margin of error. But for now, just think about the intuition about what that margin of error represents. So here's the statement. 52% of Americans support Todd Gabe for president, plus or minus 4%. And that margin of error accounts for the fact that this 52% came from a sample. And if you had contacted or asked a different group of people whether or not they supported Todd Gabe for president, you would likely get a different value, different percentage. And this margin of error sort of accounts for the range of percentages that you might get from different samples. Another common application of statistical inference is to use information from a sample to test a claim that you might have about a population proportion. For example, I've always believed that more than 60% of college students hum along to Taylor Swift songs. I know that I certainly do. Anytime a T-Swizzle song comes on the radio, I'm not just humming along, but I'm like rolling down the window and sticking my arm out and I'm singing and going, woo, 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 T-Swizzle in the house. So the way that I might test this claim that I have about all college students, because of course I don't have access to every college student, is I might collect information on a random sample of college students, calculate the proportion that would claim to sing along to a Taylor Swift song. I would then compare that sample percentage to the 60% that I have for my claim, and then ultimately I'll be able to decide if there's support for my claim or it's possible I'd have to reject the claim that I have about all students. So whether we're using information from a sample to estimate a population proportion value or to test a claim that we might have about a population proportion, ultimately we're using data from a sample. So because of that, when we do statistical inference, we use what's called a sampling distribution. And specifically, since we're dealing with proportions, we use a sampling distribution of sample proportions. So in a second, I'm going to show you what I mean by a sampling distribution of sample proportions. But let's start with the assumption that 40% of all university students eat lunch in the union. Who could blame them? I mean, unions have nice food courts. They usually have salad bars and delis and all sorts of good stuff. So you can't blame students for wanting to eat their lunch in the union, but let's assume for now that it's 40% of all students. So we can take random samples out of the population of all university students, and we'll take samples of 30 students and record the proportions that we find. So if the true population proportion is 40%, when we take a random sample of 30 students, we're likely to get values that might be around 40%, maybe a little bit less than 40%, maybe a little bit more than 40%, again, depending on the exact people we have in our samples. And we can take all these proportions we get from all these different random samples of 30 students, and we can plot them on a histogram, and that's called a sampling distribution of sample proportions. Here's a sampling distribution, and remember for the underlying population, 40% of all university students eat lunch in the union, and this shows the proportions we got from random samples of 30 observations. So there were no samples where the proportion was between 0 and 4%, or 5 to 9%, or 10 to 14%, or even 15 to 19%. There was a small percentage where, based on our sample size of 30 observations, the proportion was between 20 and 24%. But when you look at this histogram, you see that the highest bar, which is a little bit over 30%, is 40 to 44%. And that makes sense because the true population proportion was 40%. If you move over a little bit farther to the right in the distribution, you also see that there were no samples where the proportion was 60 to 64%, 65 to 69, 70 to 74, etc. So just like with any other distribution, when we calculate a sampling distribution of sample proportions, we want to think about the shape, center, and the spread. And the sampling distribution of sample proportions has a normal shape, so that gives you a sense of what the shape looks like. The center of this sampling distribution is a true population proportion. So the population we were looking at a moment ago had 40% of all students at either union. So the center of this sampling distribution will be 40% too. And the spread, or what we call the standard error of the sampling distribution, is calculated using this formula below. It's sigma subscript p bar, where the p bar reminds us that it is a sampling distribution of a proportion, equals the square root of p times 1 minus p divided by n, where of course p is the proportion that we have from our population. So going back to the sampling distribution that we looked at a moment ago, the shape of this is certainly symmetric and it's approximately normal. The mean value of this sampling distribution is 40% because that's the proportion from the underlying population, and the standard error is 8.94%, is found by taking the proportion, which is 40%, multiplying that by 1 minus 40%, dividing it by the sample size of 30, and then you take the square root of that value.